x plus b, we can write expected value of the ax plus b, because we know that the mu and expected value is same. Then we know that from the linear combination we can write this in this form: a expected value of x plus b, or you can write it like this: a mu x plus b. Okay, just write in this form. Then for sigma 2 ax plus b is equal to expected value of the ax plus b minus a mu x minus b. Okay, power 2. Because we know that we have to write in this form: ax plus b minus mu ax plus b. We know that the mu ax plus b is like this. If you multiply a minus or a negative like this, as a result we have the minus a mu x minus b. Then we can say, okay, don't have this b, and as a result we have expected value of the a2 x minus mu x, because we know that both of them has a, can get a from this power 2. Then you can write in this form. You know that's the constant. You can, because we mentioned it here that a and b are constant, we can send it behind the expected value. Then we have a2 expected value of this x minus mu x power 2, and from this we know that this is equal to sigma 2 x. Then as a result we can write a2 sigma 2 x. Okay, and so the proof in this, we easily show that the sigma 2 ax plus b, when the a and b are constant, is equal to a power 2 multiple sigma power 2 of the x, or variance power 2 of the x. But here we have some special cases that I will show you. Okay, we can write it. No problem. E2 x minus somewhere like this. Okay, we have some special case. Cases. Okay. When a is equal to 1, we know that we have something like this: sigma 2 x plus b. Okay, means that 1 multiple x plus b, then we have something like this: sigma 2 x. And also we know that if we because at the theorem we had something like this: a x plus b equal to a to sigma 2 of x. If a is equal to 1, we can put it here: 1 power 2 is equal to 1 multiple sigma 1. But we can write it in this form. And we know that the shifting the density function to the left and right, left and right has no effect on the variance. How we can say this? Well, this. For example, we have a scale like this, and we have a variance like this. Okay, that the variance is mu x. If you consider this scale as a x, if we shift it to the right or left, what happened? Nothing. Same variance. Because, for example, if we shift it to the right, like this, we assume that they are, for example, they are at the same scale like this. For example, if you consider this as 2, it's also 2. Mu x plus b. The variance is changed? No, because we know that the variance of, for example, x is equal, for example, is equal to 2, or also is equal to. What we just shifted to left or right. Another case, if you call it bond. Another special case is when b is equal to 0. Then we can write it like this, and we can write it a to sigma x plus. Same as before, because we don't have b here, we don't have any change in order. But when b is equal to 0, we have something like this. Did you write this part?
Yes.
In this case, when b is equal to 0, means that we don't have any shifting to right or left, but we have to consider the a here, because a is multiplied by the variance. What happened here? For example, if you consider this variance, x, consider this as x. When a is less than 1, we have a variance like this, smaller variance, because, for example, if you consider the variance as a 2, If you multiply, for example, 0.5 by 2, means that as a result we have a smaller variance. But what happens when A is more than 1? Of course, that when A is more than 1, it means that the value that we will multiply by this sigma or the variance is greater than 1. Then, as a result, we have larger variance, like this. Larger. Then, with these special cases, we understand that if we change the value of the A, we directly have some effect on the variance by finding the smaller variance or larger variance. But if we change the value of the B when A is equal to 1, we don't have any changing in the variance, but we have some shifting to the right and or to the left. We can show it, for example, for mu x minus b by this form. Minus b. We just shift the variance in the right and left. Okay. The last theorem that I want to talk about it today is consider x and y be a joint distribution function of the f, x, y. Means that we have the x and y as a distribution function of f, x, y. Then we can write a variance like this: x, ax plus by is equal to a2 sigma 2 x plus b2 sigma over 2 of the x plus 2ab sigma 2 xy.
Sorry, if I ask you, the b squared is sigma, is it x also or y?
Excuse me, it's y. Yeah, sorry. A power a multiple variance of the x power 2 plus b over p over 2 multiple variance of the y over 2 plus 2ab variance power 2 of the x and y, both of them. Okay, now we can prove it like this. Similar to the previous one, first we compute mu ax plus b1. Remember, similar to the previous one, first we have to find this. How we can find this in this form? Mu ax plus by is equal to expected value of the ax plus by. We know that we can write this in this form. A expected value of the x plus b expected value of the y, or we can write it in this form. A mu x plus b mu y. Okay? First we found this one, and then for sigma 2 xy ax plus by, we have something like this. Expected value of the ax plus by minus this a mu x plus b mu y. Okay, power 2. First we know that we can put mu ax plus by, and when we found the mu x plus by, we can put this instead of that. Then can write it in this form. You know that we have, if we multiply this, if we multiply the ax plus by to this, finally we can find a2x minus mu x plus b by mu y. Okay. Alright. This by this, this by this. Okay. Then we can write it in this form. The expected value of the a power 2, this 2 x minus mu x power 2 plus, because from the linear combination of random variable we can, you know that we can write it in this form. Expected value of this part and expected value of this part, but we have to consider this power 2 plus expected value of the b2 y mu f by power 2. Okay? Now we have to find this part. And as a result, we have to write this e to ab x minus mu x y minus mu. Because we know that when we apply this power 2 to this, we found this, and this. Then we can find the expected value of each of them. Okay, is equal to, from this part we can write a2 sigma x2 from this part plus b2 sigma y power 2 from this part plus, we know that's the constant, you can send it here and write 2ab sigma to xy. Okay? We proved that theorem by found the mu and variance on the sigma of the joint function, joint distribution function. Okay? You know that we have this for it, and we have two corollaries. If x and y are independent, then we can say that 2xy is equal to 0. So sigma to ax plus by is equal to a2 sigma to x plus b2 sigma y plus 2. Because we know that when x and y are independent, sigma over 2 of x and y is equal to 0. If you put 0 here, 0 multiplied 2ab is 0, then we can write just this part. And you have to notice that if b is equal to -1 and a is equal to 1, as a result we have x minus b, because b is equal to -1, x y. Okay, then we have sigma over 2 minus sigma y over 2, and the last one is like this. Corollary. If x1, x2, xn are independent, then independent random variable and if x is equal to summation of from car to n x a car, we have x1, x2, 2, still x, not u. xn are independent random variable, and if the x is equal to this summation of these independent random variables, then we can say that sigma x2 is equal to x car, because we know that the x is equal to summation of the x car. Then we can say that sigma or variance of the x bar 2 is equal to summation of variance power 2 of the each x come, maybe 1, 2, 3, 4 until end. And it was the last thing that I had planned to talk about this. And Pythagoras Shahab will talk about the other topics next week. Do you have any question? If you don't have any questions, the end of this lecture.